Welcome to Cambridge IGCSE Physics, Lesson 51.1, Structure of the Atom. Today we explore the fundamental building blocks of matter, examining how atoms are constructed with a positive nucleus and orbiting electrons. This core content lesson forms the foundation for understanding atomic physics and prepares you for Cambridge IGCSE examinations. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe atom as positive nucleus with electrons in orbit. This means understanding the basic structure where negatively charged electrons move around a positively charged central core. Second, understand most of atom is empty space. This concept reveals that atoms are mostly vacuum with particles occupying tiny volumes. Third, no nucleus is very small compared to atom. The nucleus contains almost all the mass, but occupies an incredibly small fraction of the total atomic volume. These objectives align with AO1, Assessment Objective 1, which tests scientific knowledge and understanding. Now let's define our key vocabulary. Each term is essential for understanding atomic structure. First, atom, which means the smallest unit of matter that retains chemical properties. Atoms cannot be broken down by chemical means. Second, nucleus, pronounced nucleus, which means the dense, positively charged center of atom. The nucleus contains protons and neutrons. Third, electron, which means negatively charged particle orbiting nucleus. Electrons have negligible mass compared to nucleus. Fourth, orbit, which means path, followed by electron around nucleus. Electrons move in specific energy levels. Understanding these terms precisely is crucial for Cambridge IGCSE success. Remember to use SI units, the International System of Units, in all calculations. Let's explore our first core concept, the atomic structure model. The fundamental principle states that atoms consist of positive nucleus with orbiting electrons. This model explains how matter is organized at the smallest scale. Key features include the nucleus contains protons with positive charge, electrons orbit in specific energy levels around the nucleus, and the overall atom is electrically neutral. Charge balance is maintained because the number of protons equals the number of electrons. The diagram illustrates this structure clearly. The red center represents the positively charged nucleus. The blue dashed circles show electron orbits or energy levels. The small blue circles represent electrons, labeled E- for their negative charge. Notice how electrons are distributed in different orbital levels around the central nucleus. Now we examine atomic scale and empty space. This concept reveals the incredible size differences within atoms. The nucleus diameter is approximately 1 times 10 to the power minus 15 meters. That's 0.000000000000001 meters. The atom diameter is approximately 1 times 10 to the power minus 10 meters, or 0.00000000001 meters. The ratio shows the nucleus is 100,000 times smaller than the entire atom. This means over 99.9% of atomic volume is empty space. To visualize this scale, imagine if an atom were the size of a football stadium. The nucleus would be like a marble placed at the center. The diagram illustrates this concept. The large black circle represents the atom boundary at 1 times 10 to the power minus 10 meters diameter. The tiny red dot at center represents the nucleus. Blue dots show electron positions in the vast empty space surrounding the nucleus. Let's work through our first example, calculating atomic scale ratios. The problem states, calculate ratio of atomic diameter to nuclear diameter. We are given atomic diameter equals 1.0 times 10 to the power minus 10 meters, and nuclear diameter equals 1.0 times 10 to the power minus 15 meters. We need to find the ratio of atomic to nuclear diameter. Step 1. Write the ratio formula. We use ratio equals atomic diameter divided by nuclear diameter. Step 2. Substitute the values. We write 1.0 times 10 to the power minus 10 meters divided by 1.0 times 10 to the power minus 15 meters. Step 3. Calculate using index laws. When dividing powers of 10, we subtract the indices minus 10 minus 15 equals plus 5. So we get 1.0 times 10 to the power 5. Step 4. State the answer. The atom is 100,000 times larger than the nucleus. Example 2 applies volume calculations to find empty space percentage. The problem is, calculate percentage of atomic volume that is empty space. The data shows atom radius equals 5.0 times 10 to the power minus 11 meters, and nucleus radius equals 5.0 times 10 to the power minus 16 meters. Now we analyze systematically. First, calculate atomic volume using sphere volume formula 4/3 pi r cubed. Atomic volume equals 4/3 pi times 5.0 times 10 to the power minus 11 cubed, which equals 5.24 times 10 to the power minus 31 cubic meters. Second, calculate nuclear volume similarly. Nuclear volume equals 5.24 times 10 to the power minus 46 cubic meters. Third, find empty space volume by subtracting nuclear volume from atomic volume. Since nuclear volume is negligible, empty space approximately equals atomic volume. Fourth, calculate percentage empty space divided by total volume times 100% equals 99.999%. The graph shows this dramatic difference in volumes using logarithmic scale. Mathematical skills are crucial for atomic physics calculations. Scientific notation, also called standard form, is essential for handling extremely small atomic dimensions. Let's examine 3 key skills. First, converting to standard form. When we write 0.0000000001 meters, we count decimal places moved to get 1.0 times 10 to the power minus 10 meters. We moved the decimal point 10 places to the right, giving the negative index. Similarly, 0.00000000000001 meters becomes 1.0 times 10 to the power minus 15 meters, moving 15 places. Second, multiplying powers of 10. When multiplying, we add the indices. 10 to the power minus 10 times 10 to the power 5 equals 10 to the power minus 10 plus 5, which equals 10 to the power minus 5. Third, dividing powers of 10. When dividing, we subtract the indices. 10 to the power minus 10 divided by 10 to the power minus 15 equals 10 to the power minus 10 minus 15, which equals 10 to the power plus 5. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, state the charge on the nucleus of an atom. This tests your understanding of fundamental atomic structure. The answer requires you to identify the electrical property of the nucleus. Question 2 is intermediate level. It states, calculate how many times larger an atom is than its nucleus, give an atom diameter 2.0 times 10 to the power minus 10 meters and nucleus diameter 4.0 times 10 to the power minus 15 meters. This requires you to apply ratio calculations using scientific notation. Question 3 is advanced level. The question is, explain why most of an atom is empty space using evidence from atomic dimensions. This tests your analytical skills and ability to use evidence to support scientific explanations. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world through atomic structure applications. Let's see how today's concepts apply in practice. In medical imaging, X-rays interact with atomic electrons to create body scans. The X-ray photons are absorbed differently by atoms with different numbers of electrons, creating contrast in medical images. Dense bones contain atoms with more electrons appearing white on X-rays, while soft tissues appear darker. In electronics, computer chips manipulate electron flow in atomic scale circuits. Modern processors contain transistors just nanometers wide, where individual atoms matter for device performance. Engineers must understand atomic structure to design these microscopic components. In materials science, understanding atomic structure enables new material design. Scientists arrange atoms in specific patterns to create materials with desired properties like strength, conductivity, or flexibility. These applications show why atomic physics matters. Career-wise, nuclear medicine uses atomic physics for diagnosis and treatment, semiconductor engineering designs electronic devices, and materials research develops new substances for technology advancement. Let's review the solutions systematically. For question 1, the answer is, the nucleus has positive charge due to protons. This is correct because protons carry positive electrical charge and are located in the nucleus, making the overall nuclear charge positive. For question 2, we calculate the ratio by dividing atom diameter by nucleus diameter. 2.0 times 10 to the power minus 10 meters divided by 4.0 times 10 to the power minus 15 meters. Using index laws, this equals 0.5 times 10 to the power 5, which equals 50,000 times larger. For question 3, we explain using evidence. Nucleus diameter approximately 1 times 10 to the power minus 15 meters, atom diameter approximately 1 times 10 to the power minus 10 meters. The ratio shows nucleus occupies tiny fraction of atomic volume, leaving 99.999% empty space. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn method marks for correct approach. Second, include units in every calculation step. This is essential for full marks in Cambridge IGCSE. Third, use scientific notation for very large or small numbers. Fourth, understand command words. State means give a fact. Calculate means show numerical working. Explain means give reasons with evidence. Let's summarize today's lesson on atomic structure. The key points to remember are, first, atomic structure consists of a positive nucleus with orbiting electrons. The nucleus contains protons with positive charge, while electrons with negative charge orbit in energy levels around the nucleus. This model explains how atoms maintain electrical neutrality and chemical properties. Second, scale relationships show the nucleus is 100,000 times smaller than the atom. This incredible size difference means atomic dimensions span from 10 to the power minus 15 meters for nuclei to 10 to the power minus 10 meters for whole atoms. Third, over 99.9% of atomic volume is empty space. This counterintuitive fact reveals that matter is mostly vacuum with particles occupying tiny fractions of total volume. For further study, review scientific notation calculations to handle atomic scale numbers confidently. Practice atomic scale problems to build mathematical skills. The next lesson covers radioactivity, which builds on today's work by examining nuclear processes and particle emissions. Ensure you understand atomic structure before moving forward, as radioactivity involves changes within the nucleus we studied today.